Okay, this is Power of the Test, Part 2. So the next step in figuring out what was going on is to find beta. Recall previously we found the critical sample mean for our two different scenarios. In that situation, we're saying, okay, well, what if the null hypothesis is true? What's the likelihood we will declare statistical significance and be wrong, right? That's alpha, that's type 1 error. Now we're going to beta. What's the likelihood that we will say there's nothing interesting going on, we're going to fail to reject the null hypothesis, but we should reject it? You can think of type 1 as, well, suppose the null hypothesis is true. These are all a bunch of the conventional averages we'll see, and that's typically what you can describe this scenario as, but we might randomly select one of these over here, these sort of green color ones. Beta is all about saying, well, let's suppose the null hypothesis is not true. Most of the time, you're going to get something that's a bit strange, that's saying, no, this is unusual, this is an improvement, this is different. But someone at random might say, no, it's exactly the same as before. This might be a little different, but not statistically significant. So in other words, in order to calculate beta, we're going to assume the sample average is different from the population. The truck does actually haul more. The new system processes orders faster than previously. So let's go through scenario A, the stronger truck. Let's imagine that when you run your 9 trucks and you see how well they do, that your sample average is right here. If indeed this is an improvement, the best guess of what the new average is going to be whatever your sample average is. That's the only information we have. So we can imagine an alternative normal distribution, just like so. Where again, here's our critical sample mean, and here's our sample average. Now the normal distribution is centered on the sample average. Again, we're assuming your sample average is the new population average, because we're assuming that there's a completely new population to be drawing from. We're assuming that these trucks are fundamentally different than these trucks. We're now wondering how many standard deviations is the critical sample mean away from the actual sample mean. That's important because we're trying to find the area of the curve. This area will be our power. If other people run the experiment, they also reject the null hypothesis, well, that's what they should do because it's different. Right? And that's what power is. However, if they're too low and they're over here, this is by definition beta. This is saying, oh, it's not high enough, they're not hauling enough to claim it's really different, and therefore this is not an improvement, they're wrong. Because again, under this scenario, we're assuming that these trucks are an improvement. So here's our information, just like we had before. Let's assume that we got 8.6 tons that we're able to haul. Our new sample average out of those 9 is 8.6. And we had about 8.5 for our confidence. So this is the equation we run. It's exactly like a z-score you might have seen before, except now 8.6, our sample average, is our population average, and 8.4935, our critical sample mean, was our old sample mean. And you do the math and you get negative 0.355 standard deviations below the mean. In other words, we need to figure out what this area is based on the fact that we're going 0.355 standard deviations below. Now, if you have a z-table, you can just look it up. But I like to put it into Excel. Excel has a command called normSdist. This is a normal distribution, and that S means it's a standard normal distribution. Standard normal distribution is what z-scores are based off. It's a mean of 0 and a standard deviation of 1. We're going negative 0.355. Negative 0.355 standard deviations to the left. And if you put that into Excel with the equal sign and everything and hit enter, it'll output about 0.361. What Excel is doing is it's taking this particular distance and it's telling us the area below. So it's going to tell us beta here. It always takes the value and below. That means our beta is about 0.361 and our power is 1 minus that, or almost 0.64. There's a 64% chance that if someone repeats our experiment, they'll get the same result. They will confirm, indeed, our truck is an improvement. All right, let's do faster processing. Similar story, now alpha is on the left side rather than the right side. Let's assume that we got a sample mean of about right there. Thus, we have an alternative. Again, this assumes our system is better, is faster. Right, takes less time. And here's our critical sample mean as usual. And we're wondering how many standard deviations is it? This becomes our power, because this is the area where if you get less than the critical sample mean, you will indeed confirm that this is an improvement. If you get more than the critical sample mean, you will say, no, this isn't an improvement when, again, assuming it actually is. You will make type 2 error. This is our beta. Let's suppose that you have this information and it turns out that it takes 3.2 hours to do the processing. Critical sample mean as 3.5. Hey, guess what? Turns out it's statistically significant. But if other people try to repeat this, will they come to the same conclusion? What's the power of the test? So why don't you pause the video, calculate it yourself to try to figure out what our new z-score should be. All right, you should have gotten about 0.1. Notice this is positive. We're going to the right. 0.1. Again, here's our sample mean. Here's our critical sample mean. So we're treating the sample mean as our population, and this is our critical sample mean as usual. Treat it as our sample mean. It should get about 0.1. Again, we'll put it into Excel. Notice now positive, right back into the standard normal distribution. And it should output 0.54, thereabouts. This is where sometimes people get a little confused. Before, the value that it outputted was beta, because before beta was on the left. But now power is on the left, and Excel doesn't know what it's calculating. It always knows it's just calculating this value and lower. When an improvement is signified as a lower value, what Excel outputs is 0.54. In all likelihood, if you're using a z-table, it's a similar situation. It's going to tell you what is the value at this level or lower. What is the area under the curve at this particular value and less than that. That means our power is 0.54, 54% chance roughly that someone will get the same result we will, and a beta of 0.46. That's kind of high. That's pretty high. The other one was pretty high too. There's a pretty strong chance that if someone repeats this experiment, they will incorrectly claim that this is not an improvement. In general, here, both of them side to side, you notice that the beta is always closer to the middle. The powers are always at the end. Because again, in these one-tail tests, in these improvement tests, over here, a lower number indicates an improvement. Over here, a higher number indicates an improvement. Couple of last points. If you increase alpha, you decrease beta. And you can see that here. Imagine you have a lower standard, what it means to declare statistical significance. So if you shift this dotted line over to the right, beta will fall. Alpha will increase, beta will fall. It works the other way. If you have a very high standard for yourself and say, I'm only going to declare statistical significance at 99.9% confidence, the beta will be huge. Alpha plus beta does not equal 1. It can equal 1, but you can see in our previous examples that they equaled less than 1. So don't think that just because power equals 1 minus beta, that alpha equals 1 minus beta. That's not true. Power always has to equal 1 minus beta because power plus beta is this whole area under the curve. But alpha plus beta can be less than 1, it can be greater than 1, it can equal 1, but it doesn't have to. Thanks for watching.